All right, today we're going to go over this will be the first part of the solutions homework answers to chapter 16. We're actually going to be two parts, 2 weeks that cover chapter 16, and this is the first week. And so this is the first part of that. And the first problem we'll be working on is number 2. Number 2 states, it's weigh-in time for the local under 85 rugby team. The bathroom scale used assesses the eligibility can be described by Hooke's law, and it's depressed 0.75 centimeters at a maximum load of 120 kilograms. So the maximum here is x equals 0.75 centimeters, and that's with a load, a mass of 120 kilograms. And the question here is, what is the spring's effective spring constant? And then the second question is, a player stands on the scale and depresses it by 0.48 centimeters. Is he eligible to play? Okay, so in order to do this, first I converted this mass to a force, and if you do that, you get 1176 newtons. And then you remember that force is equal to a negative spring constant times the change in x. And so we want the spring constant, so that's going to be equal to F, a negative F over x, and x it's depressed, so that's a negative number, so K is going to equal 1176 divided by, and you can do this either keeping centimeters in this case, or more correctly using meters. You're going to put 0.0075. Okay, that's meters. And then your answer is going to be 1.57 times 10 to the 5th newtons per meter. So maximally loaded, the spring constant here effectively is there's a negative sign here too, 1.57 times 10 to the 5th. So that's the first answer. The second answer, the question is, if he depresses the spring, we have this minus 0 or 1.57 times 10 to the 5th. If he depresses the spring 0.48, so a negative 0.0048, because we're changing that to meters, then is he eligible? If you do the math here, you end up with a weight of 753 newtons. If you divide that by 9.8, you end up with 76.8 kilos, and it's an under 85, so it's a yes on that. So that's the first problem. Problem number 3. Problem number 3 states, one type of BB gun uses a spring-driven plunger to blow BBs out of its barrel. Calculate the force constant of the plunger spring that you must depress so X is going to be depressing 0.15 meters. And with that, you get a velocity. Well, wait a minute. First of all, the mass of the plunger is 0.0500. This thing's not going to write for me. Kilograms. And a velocity of 20 meters per second. So the question here is, what is the K of this spring in order to achieve this? Well, the potential energy that's generated by elastic force or elastic possibility. You remember gravitational potential energy is the potential energy that you have if you're standing up here. If you were to fall off and the force of gravity were to act on you, what amount of energy is in you because of your position in space. Elastic potential energy is if you take a spring and it's wound up, but it's not released, what is the energy that's contained in that if it were to be released? And so that is calculated with the following formula: 1/2 kx squared. So and that's going to equal, in this case, the kinetic energy of motion that the BBs will have, which is 1/2 mv squared. So the potential energy of the spring, expressed with this equation, is going to equal the kinetic energy of the BB when that spring is released. And so that means, if you eliminate the halves, that 1/2 kx squared, or kx squared, is equal to mv squared. And in this whole thing, the only thing you don't know is k. K is going to be mv squared over x squared, which is going to be 0.0500 times 20 squared divided by x squared, which is 0.150 squared. And that's going to equal, if you do the math here, it equals 8890 newtons per meter. 8890 newtons per meter. Now the second part of this question says, what force must be exerted to compress the spring? So this is A. So B is equal to, the force is equal to minus kx, which is going to equal 8890 times, and depressing the spring is 0.15 minus. And so if you do the math here, you get, so if you multiply that, you get 133 newtons. Got this off by 10, sorry, when I wrote the answer down. So that's number 3. The next problem we're going to do is number 6. Number 6 states that a spring has a length of 2, so its L is equal to 0.200 meters, and a mass of 0.300 kilograms is hanging on it. So let's call this 1 and 1. And a length of 0, so L2 is going to be 0.750 meters if you hang a mass of 1.95 kilograms. And so this difference in the masses produces a difference in the lengths, and that's how you figure out what the force constant is. And so the force constant here, so A is the same problem, F is equal to minus kx, and so K is going to equal delta F divided by delta X, and that's going to be 9.8 times the difference between these two masses, which is 1.65 kilograms, divided by the difference in lengths, which is 0.55. And if you do the math here, you get 29.4 newtons per meter. 29.4 newtons per meter. The second part, B, asks the question, what is the unloaded length? Okay, if there's no load, what would the length be? So the unloaded length is equal to the length maximally loaded minus the force required to get that maximal load divided by K. So that's going to be the maximally loaded length minus 1.95 times 9.8 over 29.4. Okay? And so that, if you do the math here, you get 0.100 meters is the unloaded length. So that's number 6. Okay, the next one's number 9. And in number 9, we're moving into a different area. These first 3 problems were Hooke's law. And Hooke's law is essentially these 2 formulas right here. This one for the elastic potential energy, and even more importantly, this one, which is Hooke's law. Okay, so now we're moving into oscillatory motion. And the key formulas in oscillatory motion are the period is equal to 2 pi square root of m over k, and frequency is equal to 1 over 2 pi square root of k over m. And what you notice here is these are the inverse of each other. That's because period's 1 over the frequency, and frequency is 1 over the period. And so these two, if you remember this one, all you have to do is take the inverse, and it's this one. And, and so these are the key formulas that you have to remember for these next few problems that we're going to be doing. So the next one we're going to be doing is number 9. Number 9 says find the frequency of a tuning fork that takes 2.50 times 10 to the minus 3 seconds to complete one oscillation. The time it takes to complete one oscillation is the definition of the period. So what it's saying here is the period of this tuning fork is 2.50 times 10 to the minus 3 seconds. Frequency is 1 over the period, which is the idea being the number of oscillations that occur in a particular time period. So for example, how many oscillations occur in a second, or how many oscillations occur in a minute, so forth. Well, in this case, frequency is going to be 1 over 2.5 times 10 to the minus 3. And if you do the math here, you get 400 per second, which is 400 hertz. A hertz is a per second. And I'm saying per second. It's a no label in the numerator and a second in the denominator. The last problem of this first group is number 12. Number 12 states the following. And this one's a little bit more challenging, I realize. And if you didn't get this, don't worry. This is not the kind of problem I put on a quiz or a test. Each piston, actually, let's skip this one. Because, I mean, if you want the answer, we'll do it in the future. But this is a more challenging problem that I just threw in there. And if you want to go over it, you can ask me in class about it. And with that, I'm going to stop and move on to something else. We'll see you with part 2 of this of these tapes, starting with number 13.